Kinetics. What is kinetics? Kinetics involves the rate at which reactions occur due to several factors. But why is it so important to understand the rate at which reactions occur? It is important to understand because this determines how long it takes for products to be produced. From this, reactions can be made efficient through things like catalysts, which we will go into later. How does each factor affect the rate of the reaction? So the ultimate way to increase the rate of reaction is to increase the number of collisions in order to have enough energy to break the bonds and overcome the activation energy. But what is the activation energy? The activation energy is the minimum amount of energy needed in order for a chemical reaction to occur. So the more collisions, the more energy, and the faster the reaction can take place. This can be shown through the collision model, which shows the relationship between potential energy and the reaction progression. This is where endothermic and exothermic reactions are relevant. Endothermic is shown to start with lower potential energy, and exothermic is shown to have higher potential energy in the beginning. But if you increase any of the factors, like temperature for instance, you increase the movement or kinetic energy, which increases the number of collisions, which are shown in the graph on the collision model. So moving on to concentration. So concentration affects the reaction rate by increasing the number of molecules, which means that the chance of collision increases. So the visual shown before you is showing two molecules that are about to collide. And so before, these molecules have a very little chance of actually colliding. But over time, to truly see how the concentration affects the rate of the reaction, we need to find the order of the reactions. So this shows us the relationship between the rate and the concentration. So the standard notation for rate order is K, which is our rate constant, times the concentration to the exponent mRn. So for instance, if our rate order was m equals 1, then that means that our concentration is whatever the coefficient was times the concentration, and then multiplied by our rate constant. So meaning that when it's first order, it's affecting the rate constant. But if the m was equal to 0, then that means that it would nullify our concentration. The concentration is not going to affect the rate order. And then if it was to the power of 2, for example, then that means that our concentration is quadrupled, which doubles our rate constant. So another factor is temperature, and so temperature affects the rate of reaction because it is the degree of kinetic energy. So as you increase the temperature, the more movement you have, meaning that there's an increase in collisions, and therefore an increase in the reaction rate. So a catalyst can also affect the reaction rate. So a catalyst lowers the activation energy. It does this through creating an alternate pathway, which allows more collisions to reach the threshold of the activation energy. So as the activation energy is lowered, the number of collisions that have sufficient energy to overcome the activation energy increases, again increasing the reaction rate. And so the reaction coordinate, which is shown on the x-axis, is something that is used to serve as a reference point for the reaction's progression. So the last factor we will be talking about today is the surface area. So the surface area also increases the reaction rate by increasing the number of collisions again. So this is shown through the example that the larger the surface area, the more likely it is for the molecules to collide with each other. This also feeds into how the orientation affects the reaction rate, because the way the molecules are positioned will also affect the chance of collisions. So as time progresses, the molecules do not collide with each other. But again, as time keeps going on, one of the molecules begins to increase, which makes it easier for the other molecule to come in contact with it, increasing the chance of collisions to happen. And so another way we can find the actual rate of a reaction, we can also look at the reaction mechanism. So a reaction mechanism is the representation of reaction on a molecular level through the elementary steps. So dissecting a chemical reaction this way allows us to find the rate determining step or the slow step. This way we can also tell what is affecting the rate. So this slow step limits the reaction. And so that's how we're able to tell what is affecting the rate. And so now we're going to move on to some examples on how you can apply all of this information to actual reactions.